Welcome back to A-Star Science, part of our GCSE Must Know Physics series. Today we're going to be talking about distance time graphs as well as velocity time graphs. Now both of them look very similar, so we need to make sure that we understand the difference between the two. Let's first talk about some basics regarding distance and velocity. First of all, we need to understand that distance is different than displacement. Displacement is used in different ways in physics. In this case, distance is the length of path traveled by an object. The length of path traveled by an object. Whereas displacement will be the shortest straight line path between two objects. Straight line path between two objects. So for example, if I put an object here, A, and then I put another object here, B, and one more, C, and someone traveled from A to B to C, finally ended up at C, that would be the distance. But once they arrive there, their displacement here, this is the displacement, which I'm going to do in blue. This is the displacement. It's the shortest straight line path. So the distance is in red, the path that they took, the length of the path that they took, but the displacement is what we have here in blue, the shortest straight line path. So now that we've understood that, let's also talk about the difference between distance and velocity. Let's just clear the board. Distance is described as a scalar quantity. It's a scalar quantity, meaning it only has magnitude. So you might say someone has traveled 10 meters. You set 10, which gives it magnitude. Whereas velocity is a vector quantity. So if you said someone traveled 10 meters to the right or downwards or east, west, so on and so on, you've now given it direction. So vectors have magnitude and direction. Distance is a scalar quantity and velocity is a vector quantity because we always include direction. And this is important for many different industries, such as one of the most important ones is in the airline and in flying, because pilots need to know, and air traffic controllers, not only what speed are planes going in, but also what direction up or down, left or right, at different angles. So let's look at this distance time graph and what does it mean. Notice you can see distance on the y-axis and time on the x-axis, and that could be any time unit and any distance unit. So when we look at the points A, B, C, and D, we have to first understand that we can calculate speed by using the formula distance divided by time. So that means for any one point, for example, this point, which I'm going to draw in red, we can calculate the speed. How? Well, we look at the distance, which for that point, the object has traveled 10 meters, divided by the time, 10 seconds, and that gives us 1 meter per second. That's a very fast object. We can also see some patterns. First, as we just said, we can see that as the line goes up, it's gone from 0 to now 10 meters. That means the object is now accelerating. It's now moving. Not accelerating, it's moving, because actually it's going at a constant speed. It did accelerate from the beginning because it wasn't going anywhere. It was at 0 meters. And now at 10 seconds, it's moving at 1 meter per second. So it did accelerate, but it started to then go at a constant speed. I know this because it's at a straight line. That was the average speed over that distance. Now, if we look from 10 seconds on at point B, the object is not moving. It's not moving at all. How do I know this? That's because the distance is not changing. It's remaining at 10 meters. So effectively, the object has stopped. It then starts to move again. And I can see that this line, C, is steeper than this line, A. That means the object is going to be going at a faster speed. And we can look at that. That's this point here. So the speed would equal the distance, which is 10 meters, over 5 seconds. And of course, that's going to equal 2 meters per second. So it's traveling at a faster speed at point C. I know this by the calculation as well as by just looking at the graph and seeing that that line is much steeper at C than it is at A. And what's happening at point D? Well, the object is returning back to its origin. It's going from 20 meters away from its origin, here, now back to 0 meters here. And that's how we use distance time graphs. So the thing to remember is that you can determine the speed of an object using a distance time graph by looking at the distance divided by the time. In other words, the gradient of that particular line. And if the gradient is 0 or flat, that means that the object is not moving. So let's look now at velocity time graphs. You can see all I've done is change the units on the side. This is now velocity, and this remains as time. But the graphs tell us different information now. Let's look at the differences. So velocity time graphs, the lines relate to whether the object is accelerating or decelerating. If we look at the line A, or the section of the line labeled A, the object has gone from 0 now to 10 meters per second, and it took it 10 seconds. That means the object is accelerating from 0 meters per second to 10 meters per second. I know this because I can see it on the graph, as well as the line is going up. At point B, the object is still moving. It's very important to understand that. That's the difference between the distance time graph and the velocity time graph. But it's moving at a constant speed. Notice it's staying at 10 meters per second. The object hasn't stopped. At C, it begins to accelerate again. And we can see that the gradient of A is less than C. So that means it's accelerating at a greater velocity. And D, we can see the object quickly decelerates. It quickly decelerates down from 20 meters per second to 0 meters per second. This is the difference between the velocity time graphs and the distance time graph. two very important pieces of information. The area under the velocity time graphs tells us the distance traveled. It equals the distance traveled by an object. Let's clear the board so we can see this more clearly. So if we look at the area underneath a section, for example, this section here, which I'm going to draw in blue, it's quite simple to figure out to calculate the area, because we know that area equals length times width, or base times height, which would equal 10 meters per second times 15 seconds, which is 150 meters. That's the area that that object would have traveled. But how about the other areas? Well, we can look at this area here, which is a triangle, which I'll put in purple. And we know from maths that area is half base times height. So if we look, it's going to be half times 10, which is the base, times the height, which is 10 as well, which is going to be 5 times 10, equaling 50 meters. And we could do that throughout the whole graph to find out the total distance traveled for the object. Challenge yourself now by pausing the video and trying to calculate the total distance traveled by the object. The second thing that we need to know using velocity time graphs, just clear the board, is that for any one point, we can calculate the acceleration. You should know that acceleration is the change in velocity divided by the time taken. So if we look at this point here, which we're going to call A, let's calculate the acceleration of the object. Its velocity changed from 10 meters per second, that was the final velocity, and started at 0 meters per second. That was its initial velocity. How long did that take? It took 10 seconds, which means that its acceleration is 1 meter per second squared. 1 meter per second squared. So at any point, we can calculate the acceleration of an object using the velocity time graph. Remember, of course, if it's a straight line, then the final velocity and the initial velocity will be the change. So there is no acceleration or deceleration. If we look at this part of the graph, we can see it's going down, and that will give us a negative number, because the final velocity, if we calculate it, will be 0. The initial velocity was 20 meters per second. The time it took was 5 seconds. That would equal minus 20 over 5, which is 4 meters per second squared. And so that object was decelerating. Even though it's a minus sign, that means it's decelerating. Please leave a comment Let us know what videos you'd like us to do. Remember to like and subscribe.